This conference will now be recorded.
Yes, good morning, everyone. Yes, very good morning. So it is audible. Online students, whether it's audible. Yes. So today we are here to see the demo of physical design, right? So when before talking about physical design, right? So whatever we are doing, physical design, it will be functional design or it will be functional verification or layout, anything whatever we do, it is only for purpose of what? Fabricating IC. Only for what? Purpose of fabricating IC. What is IC? IC is a integrated chip. So nowadays, when we talk about IC, right, integrated chip, it has millions of cells or millions of gates inside. Right? We are in the era of what? VLSI, very large scale integrated circuits. So we have millions of gates on a single chip. So where this IC is fabricated? See, we have a IC for mobile phone application. Right? In each and every mobile phone, we have IC. Right? We have IC for mobile phone application. Right? This.
Yes, sir.
So, and my question is, where is IC is fabricated? See, IC is fabricated in a place called as foundry. It is fabricated on silicon die, right? That we everyone know. But where it is fabricated? It is fabricated in foundry, right? So IC is fabricated in IC is fabricated in foundry. So foundry, when we have to fabricate IC in foundry, foundry is a place which should be very clean and neat because the transistors are in the size of nanometer. It is 10 to the power of -9. So to see even a single transistor, we want to use some complex microscopes. We cannot see through our eyes. So small piece of dust or small chalk powder, right? It can cover hundreds of transistors. So I see the foundry should be very neat, it should be very clean, and it should be very sophisticated. In foundry, what happens is, so more than the knowledge of electronics, you should be now having the knowledge of chemical reactions in the foundry. So wherever the electronics engineer are present, right, they don't have much role in foundry because having more knowledge about rather than having more knowledge on electronics, you should be having more knowledge on chemical reactions because you want to fabricate an IC means you have to do some process like masking, etching, right, removing the oxide layer, ion implantation, diffusion. So there you want more chemical knowledge rather than electronics knowledge. Then why electronics engineers, where they have jobs when they don't have in foundry? Foundry IC is fabricated, but I tell that more than having a knowledge about electronic circuit, you should be having more knowledge about chemical reactions. Then where we have jobs? See, we have jobs in IC design, right? What we do is we have jobs in what? IC design. So we are involved in IC design. See, when I send any IC, for example, a company sends IC for fabrication in foundry, right? I told the foundry is to be very sophisticated place. You see, it should be 100 times or 1,000 times neater and cleaner than the operation theater in the hospitals. The water what they use is it should be highly what, purely distilled water. So the investment to form a foundry is very huge. And if you want to get your IC fabricated, right, even the company also should invest very huge in that. So once a IC comes out of a market, right, its cost will be, for example, a company has invested like 10 crores in fabricating an IC, right? Once a IC comes into the market, right, its cost is not even more than 2,000 rupees. I'm talking about IC which is used for a mobile phone. It's not even more than 2,000 rupees. When he has to meet that 10 crores, how many ICs he has to sell in the market? So if the mobile phone company or the IC fabricating unit, right, or mobile phone unit, if they have to purchase IC from the mobile phone, that is a foundry or from a company, right, they have to trust them. IC should never fail. So IC should work in terms of, right, it should be having, IC should take less area for IC, it should be having less power consumption, right, high high operating frequency, and it should have more functional blocks. A single IC is expected to do more operations, right? The same IC, image decoding, right? Call receiving, right? Call receiving and transmitting, right? Transmitter and receiver, GPS module, Ethernet module, Bluetooth module. If all more functional blocks, right, should be present in same IC. We expect that. So if this IC fails in any one of these aspects, right, so the company will lose its market in the company will lose its market. That's it. Then the company will suffer a huge loss. So before sending the IC to fabrication, we have to see that IC is functioning properly. It is consuming less power. It's operating with high frequency. It's having less area. So we have to ensure that. So without ensuring all these things, right? If we send this IC for the fabrication to the foundry, and this IC is showing a drawback in any one of this aspect, so the company will lose the market and they will suffer a huge loss. So electronics engineers are mainly involved in designing an IC. Right? So we use EDA tools. Right? What do you mean by EDA tools? We use EDA tools. EDA stands for what? Electronic design automation tools. Right? We use EDA tools for designing IC. I think in your UG classes you have used Xilinx, most of them. That is also EDA tool, right? By using this Xilinx tool, you have designed one counter or you have designed one flip flop or mux. That whatever the bit file you get, you have dumped on FPGA, and that FPGA versus IC. So this is called as electronic design automation tool. As electronic design automation tool is nothing but a software which is going to mimic the real silicon, right? In electronic design automation tools, right, I tell that I am using MOSFET, but real MOSFET is silicon, but how I am using in the tool? So I am using its mathematical model, the silicon mathematical model, how the silicon behaves, right? We have a mathematical model for that, or current equation for that. For every device we have a current equation. Diode you take, you have current equation. BJT you take, you have current equation. MOSFET you take, you have current equation and voltage equations for that. That equations we use and we do mathematical model, and that we use in electronic design automation tool to design an IC. Right. Now whatever I discussed is like to design an IC, the foundry is responsible for fabricating IC, but we are designing an IC. Then what type of information we have to give to the foundry? I have a company, right? I have involved my engineers to design an IC, and they have designed the IC. Then what type of information I have to give to the foundry to fabricate it? Can anyone tell me what information I have to give? Whether I have to give this gate level diagram to design? Whether I have to give this gate level diagram to
Length
design?
and width of the
If I give this, the foundry can fabricate IC. For example, this is IC, right? If I give this, my foundry can fabricate, or if I give the Verilog code, the foundry can fabricate. What information I have to give for a foundry to fabricate it?
GDSII.
Yes, good, right? So we have to give a GDS file. So GDS file is required, right? We have to give GDS file. GDS stands for graphical data stream. Graphical data stream information interchange. So we have to give GDS file to the foundry, right? This we have to give to the foundry. Right. For fabrication. So the designing team, we are designing through electronic design automation tools. After designing, we will generate what? GDS file, and this GDS file will send for foundry for fabrication. This is what the foundry can understand. Foundry can understand our gate level diagrams, or foundry can understand our Verilog code or VHDL code. My foundry can understand only this one. What is this? GDS. So my question is what this GDS contains. What is GDS contains? So GDS has a layout information of cells, right? And its connection. It has, right, layout information, cells, and its connections. Everyone, I think everyone know what is layout. Layout, right? What layout has? See, for example, I'll draw one simple layout here. For example, you take an inverter, CMOS inverter. You take a CMOS inverter. You know what CMOS inverter consists of? It has VDD, and after that it has what?
ground,
PMOS.
and it has a MOSFETs,
Yes, good.
PMOS
It
and
has
NMOS
NMOS,
and ground.
NMOS, and
Both
this is
cases
your
are connected.
V in and this is V out. This is your schematic structure of CMOS. CMOS stands for complementary metal oxide semiconductor. This is a schematic structure of CMOS. It's an inverter, right? Basically, this inverter is implemented by using a CMOS. So this one, right? This information your foundry can understand. What foundry can understand? It's layout information. What is layout? A top view of a cell, right? So if I really fabricate, what is the top view I'm seeing? A top view is called as what? Layout. So how to draw the layout for this? See, I have a VDD, right? So what is VDD? In the, if I really fabricate this, what will be the VDD? VDD will be a metal layer, right? What is VDD? VDD is a metal layer. This is VDD. Blue color is metal layer. Even this VSS, whatever VSS I have, this is also metal layer. VSS. So when I want to form the PMOS, right? If I have to use either twin tub process or N-well process, whether people are aware or not, I don't know. So we have N-well process. This PMOS is always formed in N-well, right? I should use N-well, right? N-well. This is N-well. So after that, I have diffusion. What I have? Diffusion. P plus diffusion. Right? I have N plus diffusion. Right? I have this N plus diffusion. This is P plus diffusion. So P plus diffusion is used to form source and drain. N plus diffusion is to form what? Source and drain of NMOS. P plus diffusion is used to form source and drain of PMOS. And if I cross over polysilicon, this will form a what? If I cross over polysilicon, this will form a transistor.
Gate.
So this side is what? Source. This is drain. This I'll take it as source. This I'll take it as what? Drain. So this is source of PMOS. Right? This source of PMOS is connected to what? Source of PMOS is connected to VDD. Right? Make that connection. Source of PMOS connect to what? VDD through metal layer. By using metal layer, please connect it. I made a connection. So here I should be having one contact cut. Contact cut means it is connecting diffusion. Right? This contact cut is connecting your diffusion and metal layer. Right? This P plus diffusion and metal layer is connected through contact cut. And here your source. This source is connected to what? This source is connected to VSS, right? Source of your NMOS, this source of your NMOS, this source is connected to VSS. Again, you should be having one contact cut here. And here, this drain and drain is shorted, right? Drain of your PMOS and drain of your NMOS, both are what? Shorted. So this drain and drain is short through metal layer. By using metal layer, please short it. Right? And from this you take one output. So this is nothing but your V out. And this gate and gate, what is shorted, right? By using polysilicon, gate and gate we have shorted already, right? So that you take it as what? From that you take it as output. By using metal layer, you take it as output. This is your, sorry, not output, input, right? You take it as input. This is your V in. Now this structure is called as what? This structure is called as layout. So this information your foundry can understand. So this information is present in your GDS tool. Your GDS tool has layout information, right? Only this information your foundry can understand. So ultimately, we have to give this file to the foundry. You do whatever you want in between. Your circuit, you make it as what? GDS2 tool and give it to the foundry. They will fabricate IC for you. That is the ultimate role of all the engineers, all the electronic design automation engineers. So we will work on this domain only, right? You work on FPGA. Instead of creating this GDS2 file, you will create a bit file, a design bit file. That bit file you will dump on FPGA. The FPGA will work as IC. Because FPGA already the IC is given to you. FPGA means what? Field programmable gate array. Already IC is given to you, but connection is not made. Our programming is not done. LUT programming. You have to do the same process whatever we do here, but here we create GDS2 file for fabrication, but in FPGA design we create a bit file, we dump on FPGA. That is the difference. But what is the difference between FPGA and this cell-based design? This is called a cell-based design. Whatever we do now, right? What is the difference? Why can't we use FPGA everywhere? See, one of the advantage of FPGA is it can be reprogrammable again and again. So today you dump bit file for D flip-flop, tomorrow you dump for JK flip-flop. You can reprogrammable. But why we can't use FPGA? We can use FPGA only, right? Why we have to do this cell-based design?
Complex circuits are not possible in FPGA.
That may be one of the reason. See, FPGA is not optimizable. FPGA circuit is fixed. I cannot change the circuit inside. I can only change the connections. See, for example, in FPGA, I have 1 lakh cells. If I dump the D flip-flop program, how much cells D flip-flop program will use? 1 flip-flop. Inside FPGA, if I have 1 flip-flop, that is sufficient. Remaining cells are wasted. In FPGA, that is the same thing, right? For example, the example I will write here. Right? I have, this is a FPGA. I have more cells here. Whatever the design I use, that is occupying only this much, the smaller design. So this much area is wasted unnecessarily, which I cannot change the circuit, which is already fixed. Only I can change the programming. But when I do cell-based design, my design is this much, means I can create IC only for this much area, which can be optimizable. Optimizable means I can improve the design. Because after me giving the GDS file, Foundry will fabricate on top of that. But FPGA is not like that. They have already given, you cannot do anything. If you want, you use whatever you want, you use in that. Remaining thing will be what? Wasted. It's not optimizable. So for that reason, till now, right, that this cell-based design has proven, right, whatever we do now, it's cell-based design. In cell-based design, what we do? In cell-based design, we give the GDS file to the foundry, and foundry will fabricate IC for us based on the GDS2 information. Now, the question starts here. How to generate this GDS tool? What are the different types of, see, this layout is drawn from layout engineers. Who is going to draw this layout? There are separate engineers called as what? Layout engineers. Then what physical design engineers will do? So to understand this role of physical design engineers, right? So for that reason, we have to understand this ASIC design flow. We have to understand this ASIC design flow. What is PD engineers will do, right? We have to understand that. What is the role of PD engineers? From where our role starts. To understand that, we have to understand this ASIC design flow.
From synthesis to GDSI format.
Yes, correct. Our role starts from synthesis. After synthesis, not even at synthesis. Again, there are separate engineers called as synthesis engineers. They will take care about that. Right. So our role starts from synthesis. After synthesis. So before going to synthesis directly, first we'll understand what is the ASIC design flow. Then only see ASIC design flow, right, is called a semi-custom design. The ASIC design flow is also called as what? Semi-custom design. So why it is called a semi-custom design means here design starts from gate level, not from the transistor level. Right? Here we will start the design from what? Gate level, not from transistor level. So full custom design means we will start the design from transistor level. That is called as full custom design. So ASIC design flow. So we'll start from ASIC design flow. So first ASIC design flow starts with specification. The first it will start with the flow starts with the specification. Specification of IC, right? So when any company starts designing an IC, they should take what is the specification from their right, from their client, right? They have to take the specification. What is the requirement? You want IC for what purpose, sir? So what is the specification? You have to take what are the functional blocks required in your IC, right? So functional blocks required. So in this IC, what are the functional blocks required? Like you want Bluetooth module, you want Ethernet module, you have PC, you want PCI controller module, you want camera decoding and encoding module, you want transmitter and receiver module in IC. Whatever the functional modules you want, first you have to take that. Next is you can take the specifications like the IC, whatever we are producing, it is operating with what type of battery, means what is our power consumption, what is the power consumption estimated. What is expected frequency of operation? What frequency of operation you expect? Right, the frequency of operation. So it is not like they will decide at one stretch. That is like some. It is like discussion. So you are expecting this, right? We can design this IC with this frequency of operation. Whether you're okay for that, right? You have to discuss with your client, and you should you can take what are all the requirements. Like what are the functional blocks required, what is the power consumption, right, what should be the frequency of operation, and what is the area required, how much area of a chip, what type of chip you want, whether you want flip chip design or wire bond design. So that is a specification you have to take from the client first. So there the top level team will involve in this, and experienced guys will chip architecture team or experienced guys will involve in this, and they will check the specification. Now, after taking a specification, we should start implementing this functional blocks. They told, right? What are the functional blocks they have told? We should start implementing these functional blocks. So, to implement these functional blocks, right, that is called as design entry. Right? Design entry. So, design entry in semi-custom design, we are going to do from Verilog or VHDL. So, we will do in the form of Verilog or VHDL. So why this Verilog or VHDL for design entry? Why we are using this? Why this programming language came in the hardware domain? Can anyone tell me? Why is Verilog or VHDL? See, this concept of Verilog or VHDL or programming language has come in electronics because see, describing anything through its behavior is easy, but internal structure is difficult. Alright. Anything if we want to describe, right, through its behavior is easy. For example, if I tell me the operation of 2:1 mux, if I ask this, what you will do? Tell me the behavior of 2:1 mux. You have one select line, you have one signal called as I0, you have one signal called as I1, right? You have output, right? If I ask you to tell the behavior of this, what you will do? Almost everyone will tell this. Anyone who will tell I don't know the operation? Everyone knows this, right? Because when S is equal to 0, right, your Y is going to take what? I naught. When S is equal to 1, Y is going to take what? I1. So telling its behavior is easy. This is a behavior. What we have discussed now is a behavior. This is a behavior. So that is what we have learned through truth table, right? Truth table is nothing but what? Table of a behavior of a circuit. This is behavior. So if I ask, tell me the internal structure of mux, how many can you tell in the gate level? I think students can tell, but only few internal structure. I'm just giving for a small circuit. So when I take a bigger circuit, all right, describing the behavior is easy through states, different states. For example, you take a ATM machine, all right? If you want to design a IC for ATM machine operation, ATM machine only you take. So first we will divide the total ATM machine into different states. 1, 2, 3, 4 different states. First state starts with what? Card insertion, right? It starts with card insertion. After card insertion and applying the pin, right? After card insertion applying the pin, it will go for the next state. After applying the pin, it will ask for what? It will ask for one state you have is called as reset state, right? It's a reset state. It will ask for a pin. So pin is done, right? It will ask for what? How much amount you want, right? If you enter the amount, it's okay. If the amount is not entered within a time, it will go back for the reset state again. If you enter the amount, it will go to the next state. All right. What is the next state? Dispatching the amount. Right. After that, dispatching the amount, next state, right? What is the thing? Last state. So collect your card. After that, it will go back to what? Reset state. In any state, if you don't enter your pin for more than predefined time, again it will go back to what? Reset state. If you don't enter your amount in predefined time, again it will go back to what? So describing the behavior of ATM machine is easy through finite state machines. So now what is your role? Write a Verilog program to implement these finite state machines. Right. First to come from the top level. These are all the different finite states machines I have. So start implementing this finite state machines through Verilog program. So why we use Verilog or VHDL is describing any circuit through its behavior is very easy. All right. So for example, you have D flip-flop. If I ask internal structure of D flip-flop, so D flip-flop I have reset signal, I have clock signal, I have output Q, right? This positive edge trigger D flip-flop. How do you define it? When reset is 1, output is what? 0. Right? I'll write here. When reset is 1, right? This output Q is what? Q is 0. When reset is not 1, when reset is not equal to 1, and if you get positive edge, what happens? My Q is going to take what? My Q is going to take D. That is a D flip-flop, right? Describing its behavior is easy, but what is its internal structure? How many can you tell me? What is its internal structure through gates? Only few, right? So remembering the structure is difficult, but describing the behavior is easy. So this behavior I can easily describe through if statements, right? I have if statement. So now the thought came like I can use if statement if reset equals 1, right? What happens? Q is equal to Q assigned with right 0, else Q is equal to what? D. At the beginning you should have written here always at positive edge of clock. This operation should take place only at what? Positive edge of clock. End. So entire behavior I have written through what statements? If statements. So in Verilog we have Verilog or VHDL we have if statements, case statements, loops. For using all these things we can easily describe the behavior. So for that reason the concept of programming came into even hardware also. The reason is describing the behavior is easy, right? That is why Verilog has behavioral modeling or VHDL has behavioral modeling. Many times we use this behavioral modeling only. Data flow and structural is rare case, right? So that reason we started using this Verilog or VHDL to describe a circuit. So in design entry, what we will do? So we'll write RTL code. It's called as RTL because register transfer logic. Data is transferred from one register to another register. So RTL code is written using Verilog or VHDL. So now the design is in Verilog or VHDL form, or I can tell in the behavioral form. Right? Even it is not in the gate level form also. It is in what form? Behavioral form. Right? So after this design entry, right, then we will do functional verification, or it is called the design verification. Functional verification or design verification. So what is functional verification or design verification? See, I have described the functional blocks by using what? Verilog or VHDL. Whether this Verilog or VHDL is doing the required operation or not. That I have to verify. How do I verify? See, I have written the program for
Simulation.
Mux. Right? I have written the
Timing
yes, tell me.
simulation.
Yes, the
Timing
simulation will do.
simulation.
Yes, good. Timing simulation will do. So I have written the program for Mux. This program I have written for Mux. So the program which I have written for Mux, right? It has inputs as I0, I1, and S, and output as what? Y. So what you do is now you start applying different test cases for this design. You start applying different test cases and find what is the output. So when time you start taking the time like this, when time t is equal to 0 nanosecond, right? Your S is equal to 0 and I naught is equal to, right? I naught is equal to 0. What should be your output expected? When S is equal to 0, what is your I naught is equal to 0 and I1 also should mention, right? I1 is like, even I1 is also 0. When I1 is also 0, what is the expected output?
Y is
Y is
equal to
what? Y
0.
is 0.
0. 0.
Because when select line is 0, Y should take what? Value of I naught. What is I naught? 0. So Y is taking 0. Now apply different output. When S is equal to 0, I naught is equal to 1. Right? I1 is equal to 0. Alright. What is output? 1. Like that by applying different test cases, right? This is called as what? Test cases. Sir. This is one test case. This is another test case. Test case means applying different inputs. So I have applied inputs like this, but the result you get in name of, right, result you get in form of test benches, right? So you will apply this with respect to time. After 10 nanosecond, after 20 nanosecond, you apply with respect to time. You apply different test cases and verify what is your output. If you are getting expected output, then your design is working as a intended block, whatever the block you written. If you are getting different output, then there is some problem with your Verilog code or VHDL code. Please rectify it. Right? So this is called as what? Functional verification. So functional verification is nothing but verifying functionality of a design by applying what? Different test cases. For that reason, you have to write a test bench program. I think in few classes you have already written this test bench program. After that, you will verify test bench waveform also. Like this, right? Your S is 0 and I naught is 0, I1 is 0. What should be your Y? Y should be also 0. And still your after 10 nanosecond, even your S is 0. Right? What is I naught? I naught is 1 and it has become 1. But I1 is what? I1 is 0. What should be your Y? Y is 1. Right? Y is 1. Like that, you will verify the test bench waveforms. So your waveform is according to your intended requirement. Then your block is working properly. Your block is implementing the functionality requirement. Then you can proceed to the next step. If it is not, you are not getting the required results, then you have to revisit and you have to modify your Verilog program. So for that reason, we do what? Functional verification or design verification. So what is functional verification? See, the first question what they ask in interviews, explain ASIC design flow. So you should be knowing how to define each and every step, at least basic term. So what is functional verification? Verifying functionality
of a
of
design.
design by applying what? By applying test cases.
Test cases.
Test vectors.
Test cases or test case vectors. What are test cases? Different combination of inputs. Right? If you have 3 inputs, how many combinations you will be having? 0 0 0 0 0 1 0 1 0 0 1 1. How many
Eight,
combinations will be having?
eight,
2 power 3, right? If you have 3 inputs, how many combinations you have? 2 power 3. What is the
eight,
E?
eight,
For example, your circuit has 32 inputs, 32 different inputs, 32-bit inputs. Then how many combinations you have? 2 power 32. So 2 power 32 means how much? Right? It is like even more than thousands. Right? So I cannot apply more than 1000 test cases. Now here comes the intelligence of an engineer. So what test cases I can use so that I can cover all the functionality. Right? What test cases I can use so that I can cover what? All the functionality. That is called as functional coverage. What test cases I should use so that I will cover all the part of RTL code. In RTL code I have written the RTL code. All the commands in the RTL code has to be executed. So what type of test cases I should use? That is called as code coverage.
All zero, all ones, alternating zero and ones, and random.
Yes, that is for this example. Bigger examples, like you have to decide it. Intelligently, you have to decide it. What type of test cases I should use so that entire functionality is covered for the bigger circuits. What type of test case I should use so that all the commands in RTL code, right? RTL code, I have all the commands. All the commands are, or all the lines are executed. That is called as code coverage. So you should intelligently select the test cases in such a way. Right? You should select your test cases in such a way that all the lines are executed or all the functionalities covered. Right? So functional coverage is not so simple what I discussed. So for that reason you have to learn system Verilog. So for computation it is very complex. So you have to learn system Verilog, you have to learn UVM. What is UVM? Universal
universal
verifying
verification methodology.
methodology. So it has some steps how to verify, how to do functional verification for a design. If you follow this, you can have better code coverage and you can have better functional coverage. So universal verification modeling. So you have to learn this both. Then only you can become a functional verification engineer. But our role is to not to discuss this because we are discussing a demo on physical design. But just I have to give the overview. What is this functional verification and what you have to learn if you want to become functional verification engineer. See, functional verification is just a step, but design is in what form? Design is in RTL form, or I can tell it is in a BRL form. Still, this BRL cannot understand by your foundry. Foundry can understand this BRL form. So why we are writing in BRL form? Because describing the circuit is easy in BRL form. First entry by describing its BRL form. Next go to structural form, gate level form. After getting gate level form, next go to layout form. We are following step by step process. Right? So functional verification is done. After that, next step is right. What is next step? See, after that, intermediate steps are there, like RTL integration. Means one block is written by one person, right? We have many functional blocks. One block is written by many different engineers, and all the block has to be integrated. All the Verilog blocks has to be integrated. So in between, you have many intermediate steps, like RTL integration. Right? I just mentioned those steps. What are that? RTL integration. RTL integration team will integrate all the RTL code. Integrate all RTL code. because entire RTL code one person will not write. One functional blocks will be given to one person. So you write a program for Ethernet module, you write program for PCI controller module, you write program for RISC core module. And after writing the programs, right, all the programs will be integrated. That is called as what? RTL integration. They are separate program. They are going to do functional verification for that. So intermediate, again we have steps called as like a linting. So what is mean by linting? See, why I am telling this means even this your RTL code should pass through all the steps. Then only it is a better RTL code. Then only that can be forward to the synthesis. Right? What is linting? See, linting team will see that this RTL code, whatever the RTL code we have got, right, it can be synthesizable. See, all the commands in Verilog are synthesizable. Only few commands in Verilog are synthesizable. And few commands is only for user understanding. All the commands in Verilog cannot be synthesized. To synthesize a Verilog code, we have to follow some, see, for example, I'll give you one example. Right. I'll just give one example. I have input D, right? Output input D, comma clock. Output Q, right? Always at pause edge of clock. Right. So assign your Q to what? Assign your Q to D. When you get positive edge, D input will be passed to what? Q, and end the always block. Simple always. Whether this program is correct. Syntax, it is correct. But there is some problem. What is that? If I use any output in the always block, that has to be declared as what? That has to be declared as reg. You have to always, any output is used in the always block, I have to declare it as what? Reg. If reg is not declared, sometimes your Verilog code may tell it is syntax correct, but it cannot be synthesized properly. Right? Because this always block is going to form on flip-flop. Flip-flop, because we have always at positive edge of clock, means whatever the circuit I am converting to gate level, it should work only with respect to what? Clock. Clock means what? It should be a flip-flop only, right? So this circuit will take clock, whatever D input you have is a D input and this is a Q output. And it's going to form, entire thing is going to form a register. In ASIC design flow or in the design, we call flip-flop as register only. Right? So for that reason, this output has to be mentioned as what? Reg. If it is not mentioned, it cannot be synthesizable. And see, for example, I have if statement, right? Or case statement. I have case statements. In case statement, there is one statement called as default statement. Correct? At last, we use default statement. If the default statement is missed somewhere, that will result in unnecessary latch creation. If that latch creation should not happen, then the default statement should be present. If it is not present, the Verilog code will show proper result during simulation. Verilog code will show proper result during syntax. But if it is default statement is not present, this will synthesize to a latch. That is not good. So if it has to synthesize to a proper combinational circuit, then what I should use? At last I should be having default statement. So all these checks will be done by your linting team. So linting team will see that right RTL code is synthesized properly. Verify whether RTL code is synthesized properly. It can RTL code can be synthesized or not. This is what they will do. So that team is called as a linting team. So in linting team also there are some types of they'll also follow like CDC check, like class domain crossing. They'll do like clock domain crossing. So these are the different teams which comes in between before forwarding the RTL to that, because they will verify that whether this RTL can be easily synthesizable or not. If can be synthesizable, then only they will forward to us. So clock domain crossing checks they will do. After that, they will pass to synthesis team. So next major step is synthesis in ASIC design flow. See, till now the design is in what form? Till now the design is in what form?
RTL.
BRL form, right? Design is in what form? BRL form, in RTL code form. So what is synthesis means? Converting RTL code to gate level netlist. Converting RTL code to gate level netlist or gate level circuit is called as what? Synthesis. Step by step process. First we enter the design through behavior. Behavioral modeling cannot be understood by foundry. Then convert to what? Gate level form. All this RTL code, whatever we have written, convert to gate level form first. Right? So that is called as what? Synthesis. Now the question is, right? During synthesis, the question is, who will give this gate information? I have RTL code, I have to convert to the gate level form, but what gates I have to use to convert? Whether I have to use AND gate, whether I have to use OR gate, whether I have to use MUX, I have to use full ladder, what gates I have to use? So who will give this information? RTL code is there, I have to convert to gate level. What gates I have to convert? Ultimately, the design has to be converted to what gate? Right? That is an important question. So to do synthesis, there is one file called as liberty file or library file that we have to give inputs for synthesis tool. This library file or liberty file has gates information. What are all the gates you should convert? So this file we will get from library characterization team. There is a separate team called as what? Library characterization team. That library characterization team, they will draw the schematic for all the circuits, all the basic circuits. They will draw the CMOS schematic. I think a few colleges have already done this. All right, like by using mentor graphics tools likeLedit or Gedit, right, and a few but Innovus tool for cadence tool you have used Innovus. You will draw the schematic, you will verify transient analysis, DC analysis, AC analysis. So there is a separate team called as library characterization team. They will draw the schematic of each and every circuit. They will apply different inputs. They will calculate what is a cell delay. They will calculate what is a cell delay for each and every gate. See, there are a few gates called as standard cells. Like we use some standard cells like inverter, buffer, NOR gate, NAND gate, OR gate, XOR gate, AND gate, AOI gate. What is meaning of AOI gate? AND or inverter. OAI gate, D flip flop, MUX, and for sometimes half adder, full adder. Right. These are all the few gates. These gates comes under category called as what? They come under category called as standard cells. Why they are called standard cells means all these gates will be having a standard height. All gates will be having same height of a standard cell. For that reason, it is called as a standard cell. For all these cells, right? For all these cells, they will calculate what is the delay of a cell, propagation delay. They will calculate what is the power consumption. What is the power consumption? And this information they will give in a file called as a .lib file. .lib file is also called as Liberty file. It is called as what? Liberty file. Also called as library file. Right? In this library file, they will give all this information, standard cell information. So, synthesis tool requires this file, .lib file. So, .lib file has standard cell information. What standard cells I can use to implement or to convert RTL to gate level information? What standard cells I have to use? The standard cells is present in which file? .lib file, library file. Alright. So, what are all the inputs for synthesis? To perform, to converting RTL to gate level netlist, what are all the inputs? If I talk, what is the first input? One is your RTL, right?
Dot V.
Without RTL, you cannot do. So RTL is your .v or .vhd. Even it can be a VHDL file also. .v is extension for Verilog file and .vhd is extension for VHDL file. So .v or .vhd. So next is what? Next is .lib, right? .lib. So .lib is called as Liberty file, Liberty or library file. What it does? It has standard cell information, and sometimes even we have macro information also. It has standard cell information. What are standard cells? These basic cells, whatever I mentioned right now. So for these basic cells, there is a team called as library characterization team. They will find delay and power consumption, and then give in a file called as what? Liberty file, a library file, and its extension is right. The extension of this file is .lib. So my tool will take a help of this file for converting my RTL to what? Gate level netlist. So next is after Liberty or library file, one more input is required. What is that?
Constraints.
Constraint.
Yes, constraints, right? SDC file. SDC stands for Synopsys Design Constraint file. See, what is why we need constraints? See, doing synthesis is very easy if you don't have constraints, but with constraints, it's very difficult, right? So constraints means in this constraints. See, in the constraints, whatever is there, right? We will study in depth in future classes. But briefly, to understand, make you people understand, I can tell in Synopsys Design Constraint file, mainly we have timing constraints. Mainly we have timing constraints like frequency of operation. Mainly frequency of operation. Apart from that, you have many information, but generally for time being, I can tell only your frequency of operation. Even not frequency of operation, that is like I can tell clock period. So your frequency of operation means your design should work at what clock frequency. That's clock time period. You mention in what file? Synopsys design constraint file. See, synthesizing to meet this constraint is a little bit difficult. But synthesizing without the constraint is very easy. It is no role of engineers only. But synthesizing with this constraints, right? It is very, very it's not very difficult, but there is some challenging things. So if you have any constraint, then only it is difficult, or else there is nothing. See, for example, your parents tell to go to VLSI Guru, whatever the mode you want. You will book a cab will come to in front of your home, will come to VLSI Guru, and you will take a cab, you will go to your home. It's not at all challenging. It's very easy. But your father tells that go to VLSI Guru and come back within 20 rupees. Then there is a challenging. Wake up early, get ready, go to bus stand, come through BMTC bus, get down here, walk a little bit, then you reach here. The constant is what? 20 rupees. With constant is difficult. So synthesizing is easy, but synthesizing to meet this constraint is what? Difficult. You have to meet the constraints, right? You have to meet this frequency of operation. So that constraint we have to give to the synthesis tool. So you synthesize in such a way that you meet this frequency of operation and little bit timing constraint, other timing constraints, like set input delay, set output delay, and what is the uncertainty, jitter. Many things we involve in this that we'll study later. What are the other constraints we are going to give? Right? These are all the different inputs what we give for logical synthesis. These are the different inputs what we give. So output, what we get from synthesis tool? What is the output?
Netlist.
Output is gate level netlist. Then what is this gate level netlist? So even see what form it is. Like I can tell libertine.lib, rtln.v, synopsis design constraint file in right .stc. So what is? I can ask one question. What is the format of this gate level netlist? What format?
Logical.
.v, sir.
It is also Verilog file. Gate level netlist is also Verilog file. Sir, input is also Verilog file. Output is also Verilog file. Then what is the difference in that? RTL is also Verilog file, and gate level netlist is also Verilog file. What is the difference in that? See, RTL has Verilog in the behavioral format, like if statements, case statements. But gate level netlist has gates information, gate and its connections. See, I will give you one example for gate level netlist. You take this example. So to understand what is gate level netlist, so you have one AND gate. So AND gate, one pin I will call it as A1, another pin I call it as A2. I have output pin Y, right? This net is N1 net, this net is N2 net. Then output of this I will give to one OR gate. So OR gate is taking N3 net. Even this OR gate has A1 pin, A2 pin, and Y pin. This net is nothing but what is used to connect from one gate to another gate. It's called as what? Net or wire. Right? So this net I will call it as N4 net. This is N5 net and it's connected to one inverter. This is N5 net and this inverter has A pin. This inverter has A pin. It has output Y pin. N4 net is N5 net. This is N6 net. So these three gates we have. And this is N1 net is connecting to one port, right? Input port. Input port is connecting. Generally this net name and port name will be the same, right? So I'll call this port also N1, what? N2, N3, and here the output port is like N6. What is the output port name? N6. So if I write the Verilog code for this, how do I write that? So first what module? module name, right? So module name I'll give it as like test program, some test program. That is a module name. What are the inputs? N1, N2, N2, N3. Output is what? N6. So I can declare, right? What are inputs? N1, N2, N3. What is output? N6 is output. Even this is also very low program. But describing this circuit differs from RTL. If I use RTL will use Boolean equations. RTL will use if conditions or case statements to describe this. But netlist uses right only gate information. Right? Netlist should not use gate level netlist means it should not contain any assign statement. Assign statement only will form the Boolean equation, right? In Verilog, there is assign statement. Assign y is equal to a and b. If you write any assign statements outside the always block, I should use keyword called as what? Assign. So netlist should not be having any assignment statements. Netlist should not be having any always block. Always block should not be there. It should be having only gates and its connection information. That's it. That should be present in your netlist. Not anything apart from that. Only that is called as a netlist. So if I call this as, if I want to write a netlist for this, for example, this AND gate, whatever I have, this AND gate name in library file, .lib file. .lib file has this information, the cell information. This name of this cell is AND gate, and 2. And 2 means 2 input AND gate. So this OR gate has library name as R2. This inverter has library name as INV because inverter always has only one input. Now, what my netlist will be having? First, my netlist will be having for every gate. First, it will describe what is. First, it will tell what is its library name. What is the library name? And 2. Next, my synthesis tool. Every synthesis tool will give one instance name. The tool only will give. Why the instance name is required? Because in this design, I can be having many AND gates, 2 input AND gates. The library name will be the same. For 2 inputs, all the library name will be the same, right? Because in library, I have only 1 2 input AND gate. If the same 2 input AND gate, if I use 100 gates in my design, all library name will be same, right? To differentiate between one AND gate to another AND gate, my synthesis tool will give one name called as instance name. The instance name for this is U1, this is U2, this is U3. Instance name can be anything that is given by my synthesis tool. So next I have to mention what is the instance name. So instance name is what? U1. After instance name, you have port mapping. Port mapping means dot A1. Dot A1 means A1 pin of your AND gate. Open bracket. Next you mention where this A1 is connecting to. A1 is connecting to what? N1. Comma. Right? Dot A2. A2 is connecting to what? N2. Comma. This Y pin of your AND gate is connecting to what? Dot Y. Connecting to what? Net N4. It's connecting to net N4. So this net has to be declared here, right? So wire I should use here. I should use keyword called as what? Wire, and mention the intermediate net names N1, N2, N3, N4, N5, N6. Right? Next, second gate. What is second gate? What is second gate name? R2. What is the instance name? U2. Next, I have port mapping. Dot A1 pin connecting to what net? N4 net. This A1 is connecting to N4 net. Comma. Dot A2. A2 pin is connecting to what net? N3 net. Comma. Dot Y pin is connecting to what net? N5. It is done. Next, inverter. INV. Right? U3. So it has dot A. It's connecting to N5. Dot Y connecting to what? N6. End module, right? At last I have what? End module. So this is the gate level netlist. In this gate level netlist, I have only inputs declaration, outputs declaration, and wire declaration. Apart from that, I have only gates declaration and its connection. Whether connection is not there in this, see, you see here this N4 net. N4 net is connecting to output pin of what? This U1 cell. N4 is connecting to output pin of what? U1 cell. This N4 net. And this N4 net is connecting to what? Input pin of A1 cell. So then my tool can understand there is a what? There is a connection from output pin to input pin. Output pin of U1 to the input pin of what? U2. My tool can understand this, right? Again, you see here this N5 net. You have N5 net. This N5 net is output of what? U2 and its input of what? Here you see N5 is output of U2, output of Y pin and is input to A pin. N5 net. My tool can understand. Okay, it is out. This net is output of A pin and input to output of Y pin and input to A pin. Right? My tool can understand. Okay, there is a connection here. Here there is a output of this N5 net is output of Y pin and input to A pin. This is called as what? Gate level netlist. In gate level netlist, you have what cells you have used from library to form your design. And what is the connection between the cells? That is present in what? Gate level netlist. Apart from that, you should not be having any keywords like assign statements or always block, non-blocking statements, blocking statements, what you see in Verilog, right? Nothing should be present in your netlist. This is called as netlist. There is a difference between netlist and RTL. Right? So that is called as gate level netlist. That example I have given already. So netlist has what? Gates and its connection. It has mainly gates and its connection. This information is present in synthesized netlist. Right? So this netlist we will forward to which team? Physical design team. So before physical design team, there is one major team called as a DFT team. Directly will not forward to the physical design team. There is a one more team called as a DFT team. So DFT stands for Design for Testability. What is this DFT team will do? Can anyone tell me?
Verification of a design under test.
Making many
That
copies
is,
of one chip.
see what this DFT team will do is they will modify this netlist. Whatever netlist we got, right? They will modify the netlist in such a way that this after fabricating chip can be tested. See, after fabrication, right? I will give my chip to fabrication, and after fabrication, I got the chip. This is the chip. See, while fabricating, everything will not go smooth because fabrication happens in nanometer. For example, there are two metal layers which are running parallel like this. This is what I see in centimeter scale. But if I see in nanometer scale, the metal layers are fabricated like this. In nanometer scale, nanometer means it's very small. Even we cannot throw eyes, see through our eyes. So this metal layer is also fabricated like this by mistake. This is what I expect. But the chemical process has done like this. There is a shot right here. Inside there is a shot. Even that cannot be seen because in our design, this metal layer connections will be in millions. Millions means more than 10 lakhs connections will be having that. They cannot even estimate where there is a short after fabrication, I'm telling. So if this chip, if I send it to the integration in mobile phone will not operate properly. Then there is a loss, right? That is a loss. See, this is not because of problem in the design. This is because of problem in the fabrication. Because see, the etching process, right? This is a see, etching process means first my fabrication unit will form the metal layer in entire this region. They cannot form only metal layer in this region. In this region only they cannot form the metal layer. It's very difficult. See, if I give very small area and if I ask you to paint there, will you paint? It's very difficult. It's very difficult to only paint in small area. So similarly, it is very difficult to form metal layer in small area. They will form metal layer in bigger area like this. And wherever they want to form metal layer, right, they will cover through mask. This layer they will cover through mask. In this layer, I have to form what? Metal layer. I'll cover through mask and oxide layer. They'll cover through mask and what? Oxide layer. And remaining regions they will treat with high concentrated acid. Acid they will use and treat with high concentrated acid. See, metal layers will react with acid and they will melt away. So all other regions will start melting. Ultimately, I will be having only, see, these regions will not melt because I have already covered through what? Mask and oxide layer. Other regions will melt away. Other regions are removed. That is called as etching. Right? Other regions are removed. So only I will get metal layers in. So now this region, if my acid is not reacting properly, so I will get this bulk regions, right? I'll get regions like this. So etching is not like they will take a grinder and they'll grind it. The grinding can be done in meter scale, not in centimeter scale or not in millimeter scale. We cannot grind it. So they will remove through chemical process. So when they are doing through chemical process, the metal can be bulged like this in nanometer scale. This metal can be bulged like this, and intermediate, and they are seeing some shots here. So this, if this shot happens to the VDD net, this is VDD net, then this net will stuck at 1. Whatever I pass, this net will always show logic 1 because it is shorted to VDD. This is called what? Stuck at 1. If this net is VSS net, if this net is VSS net, this net will stuck at 0. So when IC is fabricated, we have to identify these faults in the IC and we have to throw that IC. It's like material testing. We have to throw the IC. So how to verify the IC? How to test the IC? To facilitate this testing, right? DFT team will add some additional logics. They'll add some additional logic inside the. Please mute it. Right? If you have any questions, you interrupt me. I'll stop. Right? So they'll add some additional logic in the netlist so that chip can be easily tested after fabrication. That is what the role of DFT team. See, their role is to make chip is easily testable after fabrication. See, testing the chip after fabrication is called as post-silicon validation after fabrication. To facilitate this post-silicon validation, there is a DFT team. So DFT team will follow different methods to add this logic. Right? So what is DFT team? Modify netlist. See, we have to modify netlist without affecting what? Without affecting the functionality. Modify netlist without affecting functionality. Okay. Modify netlist, functionality should not be affected. Whatever the functionality we have, it should not be affected. Modify netlist without affecting functionality so that the chip can be tested after fabrication. So they will modify this netlist. So they use different methods like, I'll mention the methods like scan chain insertion. right? Built-in self-test. ATPG, automatic test pattern generation. They will do this. They will modify, slightly modify the netlist. This has to be inserted inside the netlist, right? They have to insert in the netlist so that the chip is easily testable after the fabrication. See, whatever present in netlist, that only we fabricate, right? That only we will take through physical design, and that only we are going to fabricate it. Right? That is what this DFT team will do. Even this is also one of the biggest domain in VLSI, design for testability, understanding the design and inserting all these logics so that the chip can be easily testable, or we can identify the faults. We can increase the controllability or observability of the chip after the fabrication. That is the role of DFT. They will make ready design, right? They will make the design ready for what? Testing purpose. That is a name called as a design for testability. Make ready the design for easy so that chip can be easily testable. Modify the design in such a way that chip can be easily testable. That is called as DFT. So after DFT, design in what format? Design is in gate level format. Even this gate level format, my foundry can't understand. I've already told it. Foundry can understand only layout level format. Right? Layout gate means what? Only gate information and its connection. That is what netlist has, right? Gate information and what? Its connection. Even this, your foundry can't understand. Then what is our role? Means next role is, right, physical design. So what is physical design? What is physical design? I've already told that what is physical design. Converting your gate level design to layout level design.
No.
Or layout level design. Another word what we use is physical level design. Another name for layout is called as what? Physical level design. That is called as physical design. See here, everything is in the logical concept. Logical concept means what? On the text, right? Everything is in form of text. So AND gate text, and net connection is in the logical format. This net is output of Y and input of what? A1. It is a logical concept, and this net now it has to be converted to metal layer. That is called as physical, right? And these gates, whatever we have in the logical concept means like a symbol, or it can be like a description that convert into layout format. That is called as physical, right? For gate, layout format means what? Or physical format. For a gate, physical format means layout. For a net, physical format means a metal layer. So that is called as physical design. Physical design means convert gate level design into physical level design. Right? This is physical design. So what is physical design? What we do in physical design? To do physical design, what is the information we need? Prerequisite is required. So all those things we'll discuss. Right? We'll discuss after a break. Right? So we'll take a break now. Now time is 11. We'll take a break till 11:10. Right? So we'll start after 10 minutes. So we'll after 10 minutes we'll see what is physical design, what steps we do in physical design, and to do physical design, what knowledge we want, previous knowledge, right, from the UG classes, what knowledge we want, and how the
Sir,
classes
how
runs. Then you take this.
sir, how long
Yes,
it
tell
will
me.
take? How long it will take?
It may take again 1 hour 15 minutes.
Okay, thank you.
One more 1 hour. Right? See, it is like, see, in demo class you want to know what is physical design, right? Why we do this? Why we have to take up this course? And what we have to learn? See, you should test yourself whether I am knowing the basic requirements for this course. If you know, fine. If you don't know, enroll for the basics also, right? You should be knowing TCL. You should be knowing Unix. Why you want to know that? That is what we are going to discuss, right? So then only you will have understanding. So why you have to take this course? What I will do is whether I have interest in this. Then only you can decide that. So to give that information, I require one more 1.5 hour time. Not 1.5 hour, 1 hour 15 minutes. I want another. Okay, we'll take a break. We'll come back at 11:10. Yes, welcome back. So we'll continue again, right? So next we started with what is physical design, right? Converting the gate level design into physical design, physical level design. Let's see, for this physical design, we need many inputs, input files. So what are the main input files for this? The three input files we've already seen, right? One is what? Netlist. Netlist what we got from what? Where we'll get this netlist? Output of synthesis, and it will go to DFT and it will come to what? Physical design. This is the main file. This only we have to convert into layout form, right? So next is that dot lib, right? Dot lib is required. In that dot lib only we have the timing information. Library, liberty file is required. Liberty file, right? Liberty file is nothing but dot lib. Third thing is SDC, right? Dot SDC is required, but I've already told you. So what are the files we used, right? In synthesis, the three files I have used as it is. And fourth file is, right, for all these standard cells, what are the standard cells I have mentioned here? This standard cells timing delay means what? Delay means timing, right? This timing and power information is present in what? Dot lib. In dot lib I have timing and power information. But for all these standard cells, one more part is I want layout. Even I am not going to draw the layout, right? I want layout information. There is a separate team called as layout team. I think you have also drawn the layout in Innova's tool, right? In our layout LED tool in Mentor Graphics, or custom compiler. So the layout for all the cells is drawn, and this information is given in a file called as LEF file. They'll extract the information in format of what? LEF file. LEF means layout exchange format. Layout, whatever you draw, that you exchange to what? Physical design team. That file is called as what? Layout exchange format. So layout for all these cells, right? The layout team will draw and they'll give to PD team in the format called as what? LEF format. LEF stands for layout exchange format. For all the standard cells, I will get the layout in form of what? LEF to the physical design, right? So one of the input required here is LEF. So I'll mention only basic inputs required. So remaining inputs you will learn in the course, right? Layout exchange format. So now I have timing means delay information and power information in Liberty file for standard cells. For the same standard cells, I have layout information in LEF file. So we have layout information for standard cells in this file, right? We have layout information for standard cells. Next, what is required? TechLef or technology file. Right? Next is .tf file. .tf file or TechLef file. Technology file. So this technology file has, right, rules, metal layer rules, metal and wire rules. That is what present in technology file. See, what is meaning of rules? If I use any metal layer, right, in your UG classes you have studied as like lambda based rules, right? For any metal layer, you should be having minimum width. You should be having what? Minimum width. The width of the metal layer should not go below the width mentioned in .tf file. If I use width less than the width what is mentioned in TF file, my foundry cannot fabricate this. My foundry can fabricate metal if I maintain this minimum width and minimum spacing between this metal layer. I should be having one metal layer to another metal layer. I should be having what? Minimum spacing. If I maintain this much minimum spacing, then only my foundry can fabricate these two metal layers, or else my foundry cannot fabricate these two metal layers. Right? So this type of information like minimum width, minimum spacing, pitch information for all the metal layers, right? And other layers also, diffusion, polysilicon, right? Wire rules, all this information is present in what file? Technology file. While routing the design, means while connecting one standard cell to another standard cell, I have to follow, or my tool has to follow the rules present in TF file. By following these rules, right, we have to do the routing. It is like the guidelines what you have, right? You should always overtake from the what side? You should always overtake from the right side. Right? When you are taking a left turn or right turn, you should put the indicator. How you are the rules? The same rules is present in what .tf file. While routing, you follow all these rules. That rule is called as the DRC rules. What we call DRC rules. Design rule checks. DRC rules. If we don't follow this while routing means connecting one standard cell to another standard cell. If you don't follow this, foundry cannot fabricate it. Foundry cannot fabricate the IC because they have the machineries, they have the process to do. So we have to follow these rules. So this file we get from foundry. LEF we get from layout team. SDC we get from synthesis team. SDC only, synthesis team only will write this. Netlist we will get from synthesis team after going through DFT. Liberty file we get from library characterization team. There is a team called as library characterization team. From that we will get these files. So these are all the basic files what is required for physical design. So layout information is present in what file? LEF file. For all the standard cells we already have the layout. Even we need to draw the layout also. So by taking all this information, right, we end up with these steps: partitioning, right, floor planning, placement, CTS, routing. These are all the steps which we use in physical design. So first is partitioning. See, we cannot do physical design for a bigger chip. I have a netlist which is representing entire chip. For that netlist, which is having gates in millions, millions means more than 10 lakhs gates is present in a netlist like this, right? Gates level information is present in the netlist like this. So how many gates I have? More than 10 lakhs. A chip will be having more than 10 lakhs gates. So I cannot do physical design for more than 10 lakh gates. So what my chip designer will do, right? The top level designer for the physical design, he will take this entire chip, right? First he will estimate what is the chip requirement, what is the area requirement, right? And he will divide all the functional blocks like this. Okay, this is one functional block. You divide this functional block. The entire chip you divide it based on the area and based on the modules. You divide the chip. Divide the chips like this into blocks. So I have divided my entire chip into different blocks. What is that? Block A, block B, block C, block D, and block E. So he will extract separate program, right? So for every block there will be a program. So each and every block he will extract separate netlist, and this is given to one engineer. Block A is given to one engineer. Block B is given to one engineer. Block C is given to one engineer. Block D is given to one engineer. Block E is given to one engineer. So this person who is handling this entire chip, right, is called as chip top. Our team is called as chip top team. So the chip top team will first partition this entire design into different blocks, and this each and every block is given to each and every engineer to do physical design. After doing physical design, the chip top will integrate all these blocks and he'll form the chip and he'll extract the GDS for this and he'll send to the foundry. So that is called as, this is full chip, this entire chip. The full chip is formed by what? Integration of different blocks. So first step is partition, right? Partition full chip into different blocks. Why? Because full chip is having 10 lakhs, 20 lakhs gates. We cannot do physical design for that. Even my tool limit will be like 1 lakh or 1.5 lakh. My EDA tool, what the EDA tool proprietor has given, that can do physical design for 1.5 lakh cells, not more than that. So then I cannot do physical design for entire thing, right? I cannot do physical design for entire chip. So first what you do is partition chip. Partition chip into blocks. Netlist is a output of synthesis. SDC is output of synthesis. Liberty file is not output of synthesis. So Liberty file has standard cell information. It is given by library characterization team. There is a separate team for that. Their role is to characterize. See, they will get the spice models. They will get the spice models like this. They'll get the spice models like MOSFET, right? They'll get the spice models. They'll use the spice models and they'll draw the schematic. For the schematic, they'll apply different inputs and they'll calculate what is the output and they'll measure delay, power consumption and all. Right? That team is called as what? Library characterization team or PDK characterization team. All right? They will give this dot lib. SDC will get from synthesis. Synthesis engineer has to write this. LEF, layout exchange format. I already told you there is a layout team, full custom layout team. There is separate layout team again. That is standard cell layout team. The standard cell layout team will draw the layout and they will give us in form of what file? LEF file. Technology file will get from foundry because it has rules that will get from foundry. Right? So all the files will not get from synthesis. Technology file will get from foundry, LEF from layout, Liberty file from library characterization team. Netlist and SDC will get from synthesis. And even this netlist will go through what? It will go through DFT process. So what is partitioning? Partition chip into different blocks. Later you integrate all the blocks. That is called as partitioning. That chip top will do. There's a separate team called as what? Chip top team, they will do. But engineers, what engineers we go into industry, right? So we start working on block level design, physical design on block level. We start doing it. So in that, the first step starts with the floor planning. Name only tells, right? Floor planning. Floor planning means plan, right? So floor planning has different steps like create core area and die area, right? IO placement, input output placement. In the block level design, input output means it is a ports, input output port placement. Next we have macro placement. Next we have power planning. So in between we have small steps like physical cell placement. So all the small steps I ignore, because if I start discussing all those things, right, it will become a 3 days or 4 days session. In between also we have many steps. I am ignoring it. I am only mentioning main steps. So here we have power planning. What do you mean by creating core area and die area? See, for your block, even this creating core area die area is done for full chip level also, even for block also, both will do. Full chip level means he will do here, and we will do for our blocks. What is meaning of creating core area and die area means, for our block, create a core area like this and create a die area like this. So inside the core area, I am going to place my all the standard cells, and outside the core area you have one more box that is called as die area. This is called as core area. This core area. This is die area. So create like this. Create core area and die area. So in between core area and die area, we are going to place input and output of a block. That is called as ports. Ports we are going to place. Ports are nothing but inputs and outputs of a block. Right. Place these inputs and outputs. So these are all the ports. So ports are just a metal layers. Right. So I will take the signal from outside world through ports, not from outside world. Sorry. I will take the signal into the block through ports, and I will take signal outside the block through output ports. These output ports and these input ports. So you have to plan where to place input ports. So this input ports placement, creating core area and die area, should be done according to the your chip top requirement. You see here one block is of what shape? L shape. This block is of inverted L shape. Right? A block is of L shape and B block is of inverted L shape. C block is in rectangular shape. E block is in almost square shape. So you have to do the area, this area, right? You have to do according with your chip top requirement. Your chip top ask, right? According to his requirement, you have to create this core area and die area. And according to him only, you have to place these inputs and output ports. What do you mean by input and output ports? Input and outputs of your blocks, right? All the signal will come to your block through what? Input ports, and will go out of the block through output ports. That is what the first two steps is, right? Creating core area and die area, and place IO, input output port placement. So here we'll study what are all the different guidelines to place create core area and die area. What are the different methods your chip top will specify you to create core area and die area. How to create core area and die area. What are the different parameters governing that? In IO port placement also we'll study how to place IO, how to do IO port placement in tool. What are all the guidelines we have to follow? What are the process we have to follow? So all these things we will study in the course, how to place this. So next is macro placement. Next step is what? Macro placement. What are macros? Can anyone tell me? What are macros?
Odd IPs, sir.
Yes, hard IPs. See, macros are complex cells which are already optimized. Right. See, we also use some complex cells. It's not a standard cells. Complex cells which are already optimized in the design. But count of macros will be less. Right. What are macros? It is I can tell IPs. IPS means intellectual properties. These are complex cells which are already optimized. For example, you assume I want SD-RAM in my block. What I want? SD-RAM. I want 50 SD-RAM. I want what? 50 SD-RAM. This SD-RAM, 50 SD-RAM I want. Each SD-RAM is consuming, if I want to implement this SD-RAM through Verilog program, synthesize it, get the netlist. For 50 SD-RAM, each SD-RAM is taking like some 1000 cells. So 50 SD-RAM will take how many cells? 50,000 cells. Right? So this SD-RAM, 50,000 cells I have to place, I have to do optimization, means improvement in the design. I should say that what do you mean by optimizing means, right? You have to see that your design is working in a best way. It is working in a best way to meet the frequency of operation. Your design has to work within the frequency of operation, and it should consume the less power. It should be having less area. This is called as optimization. You have to improve your design. That is a main challenging task. Do physical design without any constraints means we can do easily, no problem in that. But do physical design to meet these constraints like less area, less power consumption, and to meet the high frequency of operation. That is difficult. That is challenging. Right. So I have a macro which each macro is having 1000 cells. If I start using in the Verilog code, and if I start synthesizing, and if I do physical design, and if I have to do optimization, it requires me a lot of effort to do that. Again, cell count will increase. So there is a vendor who has already done this physical design for this macro. He tells that my macro is having best power consumption, and it can operate with high frequency of operation. It's having less area. See, all the companies in this VLSI, they are not entering into fabrication. There are many companies only they will produce these macros. Then why I have to write the Verilog program for this, right? I'll directly purchase from him. Directly purchase LEF from him, right? Directly take LEF from him. Layout information of this macro, directly take from him. So this SD-RAM is having how many cells? 1000 cells. He has written the program for this SD-RAM. He has done the synthesis. He has done the physical design. After doing physical design, the layout information of this SD-RAM, he is giving in LEF file, and timing information, he is giving in .lib. Directly take that, right? And now this is one macro for me. Like that I have only 40 macro. Now what is my cell count? 40 macro. Inside that macro I am not worrying. Why? Because it's already optimized. And a vendor tells that I have already done. Connection I have done. I have implemented all the layout of standard cells inside the macro I have done. He is already giving me the LDF file. What is present inside? Why I have to worry about what is present inside? Directly take and directly do it, right? It's like a puliograph mix. To save your time. You have puliograph mix, right? So if you want to do, so you have to do many dishes from the scratch. Along with that, if you want to do puliogre also from the scratch, what you have to do? You have to put all the ingredients, right? You have to first make that puliogre, right? And you have to that mix with rice. Already puliogre mix, the MTR or GRP tells that I have the best puliogre mix, which is going to give you the best taste. Why you will do that from the scratch? Directly bring that mix and mix it with your rice. What is the advantage in that? Time saving, effort is less. The same thing, right? That is called as macros. Already the cells which are optimized, and your vendor tells that this cell is a best cell, or this cell is a best design, what we can obtain, directly purchase from him and implement use in your design. Those are called as macros. So next is you have to place the macros. First you place the macros. So why we place first macros means macro count is very less. Macro count will be like, see, for example, standard cells count will be like 50,000 or 60,000. Macro count will be like 40 or 50, less than 100. Right. So then what are macros? Macros are complex cells which are already optimized. We'll directly get LEF information and .lib information from them. Functional information will not get. For that reason, it is called as hard macro. Hard macro means we'll not know functional information. What is how this macro is implemented? What is the Verilog code for that? We don't know. Ultimately, Foundry also wants that only, right? Layout information and what? Timing information. Timing information we want because to see that whether this macro is satisfying or macro is ready to operate with required frequency of operation or not. You want timing information. Timing information means delay information of macro. Right? So that is called as macro. These are all macros. So first to place the macros. So macros are complex cells which are already optimized and circuit is fixed. Means inside layout is fixed. We cannot change that. We'll directly purchase the layout information in LEF file and we implement in our design. Right. So macro placement, to do the macro placement, we have many guidelines. So we have to understand what are all these guidelines and we have to place the macros. Then we do power planning. Why? What is power planning? Why it is required? So mainly power planning is done to reduce IR drop. Right. Mainly it is done to reduce what? IR drop. See, IR drop happens in the metal layer. For example, you assume that you have a power VDD port here. VDD port, and this VDD port is supplying a voltage of 1.6 volts. See, in lower technology at 14 nanometer, 28 nanometer, or 7 nanometer, the VDD voltage will be only 1.6 voltage. It is not like 5 volts, what you study in your UG classes, right? That is not the VDD voltage. VDD itself is 1.6 because design has scaled down. Now we are in 14 nanometer, 28 nanometer. The VDD only is 1.6 volts. Now this VDD, whatever we have, I have cells here. For this cell, you assume this standard cell, I have to connect through metal layer. I have to give VDD connection to the layout. Inside this standard cell, I have what? Layout. So this VDD, whatever I have in the layout also I have VDD, right? In the layout also I have this VDD. This VDD. To this VDD, I have to give external VDD connection. Right? Like this, I have to give connection. So here I am getting voltage of 1.6. Right? It's like this. Here you are getting voltage of 1.6. This is your port, and it is going through metal layer and it's going to your cell. It's like this. Right? This correction I read on here. Now this metal is having some resistance. Every metal layer has resistance, right? And current is flowing through this. Through metal layer, current is flowing through this. According to Ohm's law, V is equal to what? I into R. So on this metal layer, some voltage drop will happen because metal is having what? Metal is having some resistance. Out of 1.6 volts, 0.3 volts will drop here. Here only 0.3 volts will drop. How many volts will reach to your standard cell? 1.3. So out of 1.6 VDD, only 1.3 is reaching here. Remaining 0.3 is dropping on metal layer itself. So this drop increases when we have long metal layers. Means if the standard cell is very far from the port, when I have the standard cell very nearby, the metal length is what? Very less, right? Only this much length I have. Here IR drop is less, but here IR drop is more. So power planning is done in such a way that all the cells will get equal power or equal VDD or VSS without any drop on metal layers. So we have to plan our power corrections in such a way. That is called as what? Power planning. So we have to study how to do this power planning, right? So plan, right? Plan the connections, VDD and VSS connections. Connections to reduce what? To reduce IR drop. So here we'll create rings or straps, rails, right, and we'll connect it. That is called as power planning. So we have to see how to do this power planning. How to do this? What are the methods we have to use to reduce IR drop? Just now I'm discussing why this process is used, why this step. Right? How to do this? We'll study in the course. So next is placement. What is next? Placement. So what is C? Now we have placed only macros. Macros means I am not placing only macros, I am placing layout of macros. What is this? Layout of macros. So placement means place the standard cells inside, right? Start placing standard cells inside the core area. Like this. Start placing standard cells inside the core area. So what you will place here inside the core area means what you will place here. Here you are going to place layout of standard cells. What you will place here? Layout of standard cells. Start placing inside core area. That is called as placement. So placement means place standard cells inside core area. See how many standard cells you will be having. You will be having standard cells from 50,000 to 1,20,000. Right? That you have to place inside the core area. See, placement of standard cells inside core area is not straightforward, right? So while placing, you have to see that you have less congestion. Right? You should see that you are having no congestion, right? Just I'll mention the words. So what is this? You will understand later, right? In the course, right? So you should be having less congestion. Yes, sir. Count and information of standard cells we get from, right, netlist, and layout for each and every standard cell which is present in the netlist. It will pick the layout from LEF file. For each and every standard cell what we have, right, in the netlist, for that netlist it will pick the layout from what? LEF file, and it will place inside what? It will place inside the core area. My tool will start placing inside the core area. So this is called as what? Placement. So placement I should do, I have less congestion. Means what is meaning of congestion? See, I have to place a standard cells in such a way that the standard cells are routable, right? Routable means I can connect through metal layers. Right? So place standard cells in such a way that they can be connected to each other according to the netlist. According to netlist, how the connections are there, right? Like that, we have to connect each other. That is called as, right, congestion. So I should not place all the standard cells only at particular location. If I place standard cells at a particular location, what happens? In particular area, if you have more homes, what happens? You cannot put road easily, right? That region becomes very congested area. The same way, you cannot place all the standard cells. All standard cells cannot be placed at particular region. So utilize entire core area and distribute the standard cells so that the standard cells can be connected to each other. Because we don't have 10 standard cells or 20 standard cells. We have 1,20,000 standard cells, and we have to make the connections according to the netlist. Right? So place the standard cells so that you have less congestion, right? So after placement, we also will check max cap and max trans violations. So this is called as STA, whatever I'm discussing, right? This is called as STA. So we will do setup violation check, timing check, all this, sir. All these checks we'll do. We'll do setup violation check. So if these things are validated, right, we can forward to CTS. If it is not validated, we have to fix it. We have to see that these violations are fixed or these violations are in the limit. Then we can go for what? CTS. So next step is what? CTS. CTS means clock tree synthesis. Why this step? Clock tree synthesis. Why we have to build the clock tree? So here clock tree synthesis, build a clock tree. By using buffers or inverters. We have to build a clock tree. Yes, Vignesh, even if you can ask, what is your doubt?
Uh, but is there any algorithm for placements and all?
Yes, see, tool has the algorithm, right? So we have algorithms like congestion-driven algorithms, timing-driven algorithms. So yes, what is your doubt? You please tell me.
So are we going to study about the algorithm placements, or we are going to just use the algorithm?
See, we are using the algorithm. We use the algorithms. So algorithms tool has used, right? Tool is already having that capability of placing it. So we use the algorithms and we ask the tool to place, but we have to guide the tool in what way you have to place. So there are many guiding commands. So place the cells in this way. Right? We have many commands for that. So we will guide that. We will see in this course. We'll see how to guide the tool because already tool is there, right? Why we have to learn about algorithms? So we'll tell how to place how to do placement, how to guide the tool to make this placement.
Okay.
See, by using tool algorithm, we have to get the best placement. Best placement will meet all these conditions. Right? If placement is not good, it will not meet all these conditions. So to do best placement, we have to guide the tool through many commands. We have many commands to guide the tool to give the best placement. So we will study that. What are the different commands? Yes, Vinith, you can ask your questions. That is what your question. What you ask?
Yes, sir. That's my question.
So CTS stands for what? Clock tree synthesis. See, build the clock tree by using buffers and inverters. See, why we have to build the clock tree? First of all, see, clock skew comes into picture later. Right? Why we have to build the clock tree? First of all, what happens if I don't build? See, mainly I have a clock port. There is one clock port here. This clock port is supplying clock to all the flip-flops. So in design, how many flip-flops I will be having? In design, how many flip-flops I will be having? 20,000 flip-flops. For all the 20,000 flip-flops, I will be driving through clock ports. Right? This clock port, right? It is connecting to all the flip-flops. Now, every flip-flop has its own pin capacitance. What every flip-flop has? Pin capacitance. Because if you see your diagram, right, MOSFET diagram, it has source, drain, it has there is negative charge carriers in the channel, and it has silicon dioxide. On top of silicon dioxide, you have gate, and gate is positively charged. So in between, you have what? Silicon dioxide, and below silicon dioxide, you have electrons or negatively charged carriers. So this will form one parallel plate capacitor. So this capacitance we call it as what? Pin capacitance. This capacitance is called as what? pin capacitance. So every flip-flop has pin capacitance. Sum of all these pin capacitance will form the load capacitance to this port. This capacitance I am not connecting. It is forming because of the nature of these layers. So when I tell my clock is rising high and my clock is rising low, my clock is rising high, clock is rising low, means this capacitor should be fully charged. Then I can tell my clock is rising high. The capacitor should be fully discharged. If capacitor is fully discharged, then my clock is coming what? Low. So charging and discharging this capacitance, right? It becomes very difficult when we have more load on this clock port. More load means this clock port is connected to many flip-flops. If it's connected to many flip-flops, see, I am the faculty, I can handle 30 students or max to max 40 students. If I have given 20 students, 200 students, whether I can show same efficiency, then what I should do? Split the batches, right? Make a tree. I am one person, HOD, have different teachers. For each and every class, you give particular teacher, right? Like that, you have to make a tree. So like that, all the flip-flops is driven by single port. So load is very high here, capacitance load. All this pin capacitance, for example, each and every flip-flop has 0.5 Fermi-Farad as pin capacitance. For 20,000, how much Fermi-Farad I will be having? 10,000 Fermi-Farad, right? 10,000, 20,000 flip-flops I have. 10,000 Fermi-Farad will be my capacitance value. To charge this capacitance, right? This is actual clock. This is the ideal clock. But to charge this capacitance, right? My clock will go like this. When this capacitance is fully charged, then I call it as what? High. When capacitance is fully discharged, then so now my capacitance start discharging. Again charge, again discharge. Whether I have written the same signal, clock signal. Ideal clock signal is what? Square shape, but actual clock signal is triangular shape. The reason is one clock port is driving many flip-flops. One clock port is driving to 20,000 flip-flops. All the pin capacitance of this flip-flop is becoming what? Load capacitance to this clock port. For that reason, I am started losing my clock shape. For flip-flops to operate properly, I should be having minimum pulse width. Minimum pulse width means minimum on time and minimum off time. That is called pulse width. Then only your flip-flop will operate properly. Or else your flip-flop cannot operate properly. So for that reason, what we do is we will start building the clock tree. So what you do is you start splitting this entire buffer connections. What you do, entire flip-flop connections, what you do is you take from here, you take 1, 2, 3, 3 buffers use. Now this clock port is driving how many cells? Only 3 cells. So 3 cells pin capacitance will become load capacitance to what? This clock port. When it is having 3 cells, now this capacitance is reduced. This load capacitance value is reduced. This load capacitance value is nothing but sum of 3 cells pin capacitance. Now connect to this flip-flop. This buffer you connect here. So this buffer, so here net length is longer, right? If net length is wrong, again it will result in more capacitance. To split this net length, again you use one buffer here. Again one more buffer you use, right? Connect to this. This you can connect directly. Take this, right? Use one buffer, connect here. Right? Take this, use one buffer and connect here. Why I am using again buffers in between means to reduce what? Net length. If net length is more, again the capacitance will increase. Even metal also has inbuilt capacitance. If more metal length, more capacitance. To break the net length, even I should use what? Buffer. So that this transition, right? This clock transition is within some limit like this. I will be having minimum on time and minimum off time. For that reason, we have to build a clock tree. This is a clock tree, what I have built by using what? Buffers. This is called as clock tree synthesis. But when I build a clock tree, if this positive edge is coming at 0 nanosecond, But the same positive edge will not come at 0 nanosecond here. It will reach after 2 nanosecond, the same positive edge. Why? Because in between I have what? This buffer delay. Right? This buffer is having like 1 nanosecond delay. This is having 1 nanosecond delay. Then this positive edge, the same positive edge will reach to this flip-flop after 2 nanoseconds. That is called as insertion delay. So because of this insertion delay, skew will develop. Right? So all those things you have to study in CTS. See, I'll come back to that, Mahesh. Right? Please wait. Right? We are in the middle of the session. So what is CTS? CTS is nothing but building clock tree by using what? Buffers and inverters to reduce load on what? To reduce load on the clock port. So, but building cannot be happen as it is. We have to build in such a way that I have less insertion delay. Insertion delay means this buffer inserted should be less. Right? I should be having less skew. With that, I have to build what? I have to build CTS. So next to what we have is routing. What do you mean by routing? So already CTS is built now, but signals, only clock tree is built. Only clock signals are built. Apart from other signals are not built. So connect these standard cells by using what? Metal layers. Connect the standard cells by using what? Metal layers is called as what? Routing. So this connection should be happening according to the netlist. How netlist is there, right? The same type of connection should happen here. That is called as what? Routing. So connect these standard cells. See, after CTS, we have to do many checks. Right? So we have to check skew, right? Insertion delay. Again, we have to check congestion. So we have to do setup violation check. Setup and hold violation. Right. So we have to do minimum pulse width check, whether clock signal is having minimum pulse width or not. Minimum pulse width check. Right. We have to do max cap and max transition check. All these checks we have to do. See, clock latency is nothing but your insertion delay, right? So that is what we will give some target to the tool. So this much latency, this much insertion delay you have to maintain. You should not use insertion delay more than this. This is called as insertion delay. The buffer delay, right? The buffer delay and the net delay from clock port to the clock pin, that is called as insertion delay or latency. Both are same. The delay from the clock port, what I told, right? The edge I am getting here at 0 nanosecond, but the same edge I'll get at what nanosecond? 2 nanosecond. So in this, for this flip flop, the insertion delay is what? 2 nanosecond. Means from the clock port to the clock pin of the flip flop, in between how much delay you have? 2 nanosecond delay. That delay is called as insertion delay or latency. We can give some value. Okay, we can tell the tool this delay should not exceed more than 1 nanosecond. I can give this target to the tool. So my tool will try to meet this target. So this is called as right latency target. I can give this target, latency target or insertion delay target. While building clock tree, my tool will try to meet this target. So from the clock port to the clock pin of flip flop, my insertion delay should not be more than what? 1 nanosecond. It should be within 1 nanosecond. So that is called as, right, what you asked me. That is called as clock latency target or skew target. So my tool will try to meet it. So checking that whether it has met or not. That is called as checks. Right? That is what called as check, insertion delay check, skew check. Right? Target I can give and verifying that whether my tool is met or not. That is called as checks. So we should give the target. That is what. So CTS tool will build the clock tree. It will build easily when there is no constraint. If you give constraint like build the tree by meeting this skew or meeting this insertion delay, then there is a what challenging. Then there is a challenge task. See, skew is different from insertion delay that we will discuss in the session. See, what is skew? For example, see, to understand that you should be understanding lot of things, but I can understand only one thing. I can give you only one information. See, skew is always calculated between two flip-flops. This is one flip-flop and this is two flip-flop, second flip-flop. See, insertion delay means the time taken by the clock to reach from clock port to the clock pin. That is called as insertion delay. So, how much delay this second flip-flop is taking? Insertion delay. Insertion delay and latency both are same. All right. So, what is the latency for this flip-flop? Second flip-flop, one buffer delay, another buffer delay. In between, you have net delay. For example, this delay is 2 nanosecond. The insertion delay or latency for second flip-flop is what? 2 nanosecond. What is latency? Time taken by the clock edge to reach from clock port to the clock pin of a flip-flop. First flip-flop. This is the first flip-flop I have, right? This first flip-flop. It is very nearby. It is having only one buffer in between. And even net length is also small. So clock will reach very early for this. The clock reaching time is what? 1 nanosecond. So for this first flip-flop, the insertion delay is what? 1 nanosecond or latency is 1 nanosecond. For second flip-flop, insertion delay or latency is what? 2 nanosecond. So insertion delay or latency will change by flip-flop to flip-flop. Because some flip-flops are nearby, some flip-flops are far away. You will be having net delay and buffer delay in between. That is called as insertion delay or latency. The time taken by clock to reach to the clock pins from the clock port. What is clock skew? Clock skew is nothing but difference in time clock reaching to the clock pins of the flip-flop. So if I find skew between these two flip-flops, skew is always between two flip-flops. If I find skew between these two flip-flops means it is difference in time, right? This for this flip-flop, the clock is reaching at what nanosecond? 2 nanosecond. For this flip-flop, it is reaching at what nanosecond? 1 nanosecond. So 2 nanosecond minus 1 nanosecond. What is the time you get? 1 nanosecond. This is called a skew. So difference in time, the clock edge reaching between two flip-flops. Right? That is called a skew. But these two flip-flops should be communicating. That is one more criteria that we will understand later. Yes, skew is always between two flip-flops. Skew is not defined for only one flip-flop. Skew is a time difference between clock reaching to both the flip-flops. Right? Time difference. So for this flip-flop, it is reaching 2 nanosecond. For this flip-flop, is reaching 1 nanosecond. If I subtract this, whatever result I get, right? This is called as what? Skew. Right? Skew is always calculated between two flip-flops. But latency is for each and every flip-flop. For this second flip-flop, what is the latency? 2. For first flip-flop, latency is what? 1. So skew is nothing but what? Difference in latencies. I can tell, right? Difference in insertion delay or difference in latency is called as skew. This is called as, alright. So all these things you have to consider during clock tree synthesis. The skew should be minimum. Latency should be minimum. You have to consider this. So next is routing. What is routing? What is routing? Connecting all the standard cells to by using metal layers is called as routing, right? connecting all standard cells through metal layers is called as routing. So after routing, we'll do all these checks again. Again, all these checks we'll do. So along with this, right? Along with these checks, we also do important checks. Is we do DRC check. So what is DRC check? While routing, we have maintained the design rules. So I have told various design rules are present. Yes, so design rules are present in TF file. Whether while routing I have followed this, I have maintained this design rules or not. So this check we'll do after routing, right? So whether all design rules are maintained or not. Right? We do DRC check after routing. See here we are not drawing the layout. We are using layout drawn from what? Layout team, and we are connecting it. What is his name? His name. What is your name? Your name. What is your name? Rahul. Not you. He. Abdul Rahman. So you are sleeping here. Why you are sleeping? Others are sleeping. You see them. Others are sleeping. Even I sit ideally. Even I will also sleep. If you take a book and if you write down, right, you will not sleep. Right? Yes, if you're not interested, this is a demo class. It's up to you. Right? If you're not interested, you can walk out, right? I don't have any problem. It's up to you. If you're interested, you join. Not even one book you have opened from the morning. Okay, so I don't want to waste the time. It's up to you. Again. By seeing you, even I feel to sleep. Even I am also want to sleep. I want to also sleep. What I can do. That is my pay to teach like this. That is not good, right? See, I am strict. I will only take physical design. I am strict in this aspects. So this misbehaves, I will not encourage. See, you do whatever you want outside the classroom. It's okay, but coming to the class and sleeping like this and at least giving the wrong opinion for others is not good, right? We are not forcing you to come. You have recorded videos. Whenever you are free, you can see that also. We'll give that facility also. Okay, now next is right LVS. So LVS stands for layout versus schematic. So why we have to verify this layout versus schematic? Yes, a tool has capability. See, during CTS, so tool will do routing of CTS. Clock tree, it will do routing. What are all the what are the signals coming in the clock path, right? It will do routing for the clock path. For that reason only we are doing CTS early, before the routing. So tool will do right routing for the clock path, and tool is capable of estimating the real routing. So how tool calculates net delay, right? Tool has capability of estimating the real routing, even though real routing has not happened. So tool has capability. What metal layers I can use? What will be the net delay? Tool has capability of that. That is called as global routing. Estimation of real routing is called as what? Global routing. So tool has capability of that, estimating the real routing. That estimation may not be accurate, but something is better than nothing, right? So tool has a capability of that. Even though there is no real routing, tool can estimate what is the net delay. Tool can do that. And after CTS, routing happens in the clock path, not in the signal path, in the clock path. These clock signals are already routed. In the CTS stage only they will get routed. Insert buffer and they get routed through what? Metal layers. During CTS stage only they are routed. But in the routing stage, we route remaining, right, from this cell to this cell, output of this cell, that is Q, right? It will go through one metal layer, one gate, any one gate. This you route it, and from this you route it. So other signals you will route in what? Routing stage. Yes, in routing stage only signals are routed. So clock gets routed immediately after the CTS stage. In CTS stage only clocks are routed. So next is layout versus schematic. So name only tells layout. What is layout? The routed design, right? The design which is routed. The design which is routed is called as what? Layout. So here whatever we have placed inside this is not a standard cell. It's what? It is a layout of a standard cell. So here the connection happens between the standard cells, between macros, between ports in the routing stage. So all the required connections are done. Right. Now my LVS will verify this layout, whatever we have, this layout, whatever the connections mentioned in the layout is same as connections mentioned in the netlist. So netlist is considered as schematic. This is what? This is layout. So in netlist I have connections, right? This connection. What is a connection? This N4 is what? Output of U1 gate and is input to U2 gate, right? Whether the same connection is maintained here or not. Here the same connection is done through metal layers, right? So this is the output of U1 cell and it is connecting to U2 cell or not. That is verified in LVS. For that name, what? Layout versus schematic. Layout versus schematic means verify, it verifies connections in layout with netlist. If both are same, okay. If both are not same, it will throw the error. There are some shorts, there are some open nets. So few nets are not connected. Few pins are open, few pins are not connected. It will show open net or short nets. Then you have to verify why it is and you have to fix it. So if all these things are done, right, then physical design of that block is completed. Then your block will go to sign off checks. Now everything is not completed, right? Again your block will go to what? Sign off checks. So sign off checks means it will go for first IR drop check. They'll use some separate tool again, right? IR drop check. So it will go for timing check. Timing check means they will do STA, static timing analysis. It will go for timing check. Right. Next it will go for, right, physical verification. All these checks. So whatever physical design we have done, right? This physical design, entire PD, this physical design we do by using a tool called as ICC2. Entire PD, all these steps starting from floor plan of a block, from floor plan till right till routing, right? That PD we do in IGC2. We'll do in IGC2. The tool name is IGC2. It is from Synopsys. So sign off checks, right? IR drop check, timing check, physical verification, right? This IR drop check is done in Redoc tool. This is a sign off checks. It's a separate team again, right? They will do this checks. Redoc tool. So this timing check is done in prime time. Again, there is a separate team, STA team. They will do this check. Prime time. And there is again separate team called as a physical verification team. They will do this by using a separate tool called as Caliber. So Caliber is, see, all this Redoc and prime time is from Synopsys. Caliber is from Mentor Graphics. Now they are going to do checks on your blocks only. Right? If there is any changes has to be done, they cannot do that. They can only do the checks and they can suggest you the changes. Again, these changes you have to take back and you have to do the changes in your block. You have to redo your placement. You have to add some new cells in your design. Everything you have to do after taking there. See, this physical verification means even they will do DRC and LBS by using separate tool called as what? Caliper. So timing check means a timing check, they will do STA, static timing analysis. And Redoc tool will do IR drop, power analysis, electron migration check. Mainly they will do IR drop and power. So here this we will do. This. See, out of sign off checks, right? This checks we will do. So we don't have Redoc tool, we don't have Caliber. We will do this. So timing sign off we will do by using what? Prime time, right? And star RC. Star RC is used for spec extraction. So we'll do by using star RC. So this we'll do. So after this, your physical design completes for one block. Then your chip top will take your block and he will going to integrate in its full chip. Right? So this much process we have to do for a physical design. So what we have done in physical design, we have taken the layout done by what? Layout team, and we have done timing checks by library given from library characterization team, right? And we have routed the design by using metal layers, and we have done all the checks, and we are forwarding that to full chip level designer. Full chip level designer will take what? This full chip level designer, he will integrate all the blocks. He will take GDS2 file. That GDS2 file is forwarded to foundry. Right? This is the flow what the IC designers will follow. So now to do this physical design from top to bottom, you only tell me what is the knowledge required. What is knowledge required? You only tell me. You saw all these things, right? What is knowledge required? So previous knowledge what you want here is mainly you need digital basics you should be knowing properly, like what is asynchronous design, what is synchronous design, what is asynchronous reset, synchronous reset, what do you mean by flip-flop, what do you mean by latch, what is the difference, what is a negative edge triggered flip-flop, what is positive edge triggered flip-flop. These basics you should be knowing. So you should know digital basics. What is mux, what is encoder, what is decoder. Right? You should be knowing digital basics. And after this, what is required? Yes, CMOS is very, very important. What is MOSFET? Right? How the MOSFET works? What do you mean by transmission gate? Why we use transmission gate? What is CMOS? Complementary metal oxide semiconductor. How to implement different circuits by using CMOS like inverter, AND gate, NOR gate, XOR gate. What is W by L ratio? So how this W by L ratio affect your design? Right. Then what is the fabrication steps? And what do you mean by layout? How to draw the layout? And what are FinFETs? MOSFETs can be used till 14 nanometer. When we go to 14 nanometer, we are not going to use MOSFETs. We use what? FinFETs. What is FinFETs? Why we use FinFETs? What is the problem with MOSFET? Yes. That is what. Why we cannot go below 14 nanometer by using MOSFET? That is what. Why we cannot scale down? There is a concept called as drain-induced barrier lowering. If source and drain comes very nearby, right? If the source and drain comes very nearby, if the source and drain, right? This is called as channel length, right? Distance between source and drain is distance between source. Yes, please continue. Yes, please mute it when you're not talking. Please mute it. See, if this distance between source and drain is called as technology. 14 nanometer technology means distance between source and drain is what? Only 14 nanometer. If the source and drain comes very close, right? The problem happens here is you have silicon dioxide here, on top of it you have gate. So when this gate voltage is more than threshold voltage, then only we tell that MOSFET is on, or current is flowing from source to drain or drain to source. When threshold voltage, this gate voltage is more than what? Threshold voltage. Then only. But in lower technology, what happens is, even without applying gate voltage, if I apply drain voltage, I can easily pull electrons from source to drain. Because source and drain are very close. Then gate is losing the control over the MOSFET. That barrier, right? What was the barrier between source and drain? What was the barrier was present? That barrier was lowering by gate, by creating the channel. Channel was created by the gate. The barrier was lowered. Now, when the source and drain come closer, the barrier even can be lowered by what? Drain. Immediately applying drain voltage, I will see more conduction. Even this conduction was present in higher technologies, 28 nanometer, 45 nanometer. That current we were calling as a leakage current. But this leakage current becomes more in lower technologies. That no more we cannot call it as leakage current. That current has some good magnitude. For that reason, this is called as a drain-induced barrier lowering. Your drain is induced the lowering of this barrier. Earlier, gate was inducing this barrier by creating the channel. Current starts flowing from source to drain. Now this barrier is lowered by what? Drain. Drain has lowered this barrier. So this is called as a drain-induced barrier lowering. So what is this? So for this reason, we use FinFETs. Why FinFETs? So all these things you should be knowing in CMOS. This much you should be knowing in CMOS. Right? After this, right? This is not sufficient. See, whatever the EDA tool we use, right? For that EDA tool, we use Unix operating system. Unix operating system has, so you should be knowing Unix commands. If you know Unix commands, Unix you know, right? You can do the operations very fast. See, if I tell to create 10 files in a folder, what you should do in Windows? Right click, new folder, give the name. Right click, sorry, new file. Right click, new file, give the name. Right click, new file, give the name. Like that, you have to create 10 files or 10 folders. But in Unix, you can do this operation by using only one command, like mkdir, and you give 10 folder names in one command. That will create 10 folders or 10 files. For file, you have different, again, gvim, some commands are there. So like that, right? So there are few commands to do the same operation what you do in Windows, like creating files, moving folder, copying folder. Whatever you do through GUI, for that commands are present in Unix. If you know that, then you can do even shell scripting also. Right? Shell scripting means I will give you one script. If you have that script, means you can easily get input files wherever it is present. You can easily copy that. In that file I have written from where you have to copy the commands I have written. That is called as what shell scripting. In Windows, I should do that means what I should do? I should make a small video. Go to this location, copy the file from this location and come back. Right? But in Unix, I have commands for that. I can directly write the commands in one file. I can give that file to you. You can directly copy the file from that, or if you source that file, or if you execute that file. So you have Unix commands. So you should be knowing Unix commands. So Unix commands are required to create folders, to create a work environment, to copy input files. That is for that reason it is required. You should be knowing Unix. So apart from Unix, you should be knowing tool command, TCL. TCL stands for tool command language. Right? So should we say why this TCL? See, your EDA tool can understand only TCL. ICC tool can understand only TCL. If I communicate with ICC2, if I want to communicate through commands or through program, then I can communicate only through what? TCL. Right? So knowing TCL is very, very important for physical design. See, I have thousands of violations. Any one of the violation, I have thousands of violations. To fix it. By using this method, I have to fix 1000 violation means one violation at a time. First violation you fix, second violation you fix, third violation you fix. 1000 violation, if you fix one after the other, means how much time it will take. Instead of fixing one violation at a time, write the script, automated script. So this script will fix all the violations, 1000 violations. Only if you source the scripted file, that is sufficient. That will fix all the violations. So TCL will help you to do automation, right? Fixing all the violations at a time instead of fixing one by one. For that reason, we use TCL, tool command language. So these four basics are very, very important. So for that reason, we have divided our course in two parts. One is basics. In basics, all these courses are covered. So another one is advanced PD. In advanced PD, we do two projects. So basics will happen for 2 months. See this, whatever date I am telling, right? It is like it may vary 2 months, 10 days, or 2 months, 15 days, or it in 2 months only we can complete. That depends upon what is the strength, how many students are there. So 2 months basics and 4 months advance. And for if you enroll for both, right, there is a separate fee structure, and if you only enroll for advanced, there is a separate fee structure. If you are not good in basics, right, then you should enroll for what? Basics. This will go for 2 months, and advance is for 4 months. Total course duration is 6 months. So basics will happen all the days, like Monday to Saturday, and Sunday will be the holiday. Every day 3 hours basics will be done. First they will start with the digital, then they will start with Unix, then with TCL, then with CMOS. After that, we'll also do some PD basics. What do you mean by transition? What do you mean by cell delay? Some PD basics we'll do. So this is done for 2 months, and remaining thing is done for 4 months. In this, 2 projects are covered. One project we'll do with help of mentor. Another project will give for you only to do the same thing. First, we will teach with for one project. Same project you can practice with another project. We'll give 2 projects here. So complex projects we will do. It's multi-voltage design. So simple projects we will give to you. See, we will do the projects, right? We will do block level design. Block level design with cell count, right? Cell count can be 50,000 or 62,000. Right? And the macros 40 to 52 macros. One project we have 40, another project we have 52. Right? Next is the technology 28 or 14. It is on 28 nanometer or 14 nanometer. Right? And we have 6 clocks in the design. Sorry, 5 clocks in the design. Right? And one of the project what we do is it is multi-voltage design. So multi-voltage design we do in the class, and another simple design we'll give to you. Right. So this also covers STA also, static timing analysis. We do static timing analysis because static timing analysis means you should learn what is setup time, hold time, what is skew, what is latency, right? How to fix if you have violations. So what do you mean by clock domain crossing? How to handle clock domain crossings? Right? What do you mean by recovery time? What do you mean by removal time when we have asynchronous inputs? Right? All those things. What is PVT conditions? What is D rate? Everything is covered in STA. So basics, right? Basics is done for every day. So when we come to advanced part, right? In this 4 months of training, so lab advanced part is having theory. This is only for advanced part. So basics is same. Every day you have 3 hours of training. So advanced part when you come, right? For advanced part you have 3 theory on Saturday and Sunday, and you have lab. Right? Lab means working on the tool. It is from Monday to Thursday. Lab. And the candidates who are already working, right? If they want to do lab, if they are not available on the weekdays, Monday to Thursday, and for them there is a weekend lab. Weekend lab is done on Saturday and Sunday. This is advanced part. Right? In this advanced part, we will do this. So basics every day 3 hours. Every day 3 hours. Right? Till you complete this. Right? TCL and PD basics every day 3 hours. So timing, the ultimate. Shall we attend, sir? See, the course is both online and offline, both. Course is offered as online and offline, both. The same, like a meeting will be opened, what are the course going on, right? The same class will be done for offline students, and meeting will be opened like this, how I have done now. Even if I have offline students here, even online students are there, right? The course is for online and offline both. Course is offered online and offline both. The timings, admin will inform you. Right? I cannot tell about the timings. See, generally, timings will be between 9:30 to 1:30. Basics timings. So after advance, the admin will inform you. Right? Advanced timing sometimes it varies because when you have this one, right, weekend lab, so you have Saturday and Sunday as theory, right? Saturday and Sunday, the industrial experts even will bring. So the timing will vary for advanced part, but for the basics, the timing will be generally from 9:30 to 1:30 or 12:30, 9:30 to 12:30. Sometimes if more students enroll, right, they'll split into two batches. They'll make like 9:30 to 11:30 and from 11:30 to 1:30. Timing will vary. Admin will inform you about timings. See, for any doubts, right, if you have any doubts, further doubts, you can ask in your group. So for working people, I've already told you, right, there is a weekend lab and theory happens only at the weekend, Saturday and Sunday. If you want to attend basics, right, they will give you the videos. See, video facilities also there. Means, for example, you are attending the session today, by chance you have not attended tomorrow, the tomorrow class you're not attending tomorrow, or today you're not attending, the video is recorded. Whatever video we are doing, right, it is recorded. That recorded video will be uploaded in your user area. So admin will give you user area for everyone, so it will be uploaded in your user area. So you can even watch the recorded videos. That recorded video will be there for 10 days. Next 10 days. If the class happens today, for next 10 days, the recorded video will be available to you. You can watch for next 10 days. Right? After 10 days, they will remove the videos. So that recorded video is given to you. The reason is live recorded videos, right? Whatever it has happened. The reason for that is you can watch if you're absent or if you are not able to follow that day, then you can watch it later. Right? Recorded videos are given. The live recorded videos is not pre-recorded. The live sessions, what it is going on, right, that will be recorded and it will be given to the students, right? So when it will upload to the students user area, they will give you the in-skill username and password. It will be uploaded to your area, so you can watch that if you're not attended. So admin will inform you. See, if you are working professional and you cannot attend on weekdays, weekend we have separate sessions, right? Theory is on weekend only, and weekend lab is on Saturday and Sunday only. Even we have weekdays lab, that is for the students who are available on the weekdays. But for the basics, right, if you are not available on the weekdays, because it's a basics, right, we don't have separate sessions on Saturday and Sunday for the working professionals because it's a basics. We will give you the recorded videos, the live recorded videos, whatever is happening, right, we'll give the recorded videos. And even if you have any doubts after seeing recorded videos, they will assign one mentor to clarify your doubts once in a week or twice in a week. That they can do. That you can talk to the admin. He will do that. Now I told you, right, for working professionals, that advanced part we have only sessions on Saturday, even lab. But basic part we can give you the recorded videos, the live recorded videos, what is going on. So what we can do is you can go through those videos. If you have any doubts, right, we can assign the mentor twice in a week to support you. He will connect through online like this with meeting, and he will support you to clarify your doubts after seeing recorded videos. If you have any doubts, that so that you talk with admin. If more students wants If more students are working, right, then he may also support some other way. They can conduct only sessions on weekends. So please talk to the admin regarding this. See, when you enroll the course, you will get the live recorded videos. What we are doing right now, you will get that live recording videos. That live recording videos is available for 10 days. On request to the admin, even he will extend it with the genuine reasons. To tell that, so one 10 days I was not able to see the videos because of some work pressure. It will be even extended on your request. Right? The live recording videos, I'm telling, it's not pre-recorded videos. Even you will get pre-recorded videos. That is for your reference. Right? And you'll also get live recording videos. Whatever the live recording videos, what you have. See, all the placement related information, please contact to the placement department. I'll give you the number of the manager, or you ask in the groups, right? They will inform you. See, if you ask what are all the companies available, I cannot give you the list. They will give you the list. Right? You please ask them. See, because last time I saw a company in the group like Chart SI. Right? In previous we had IBM, let's say AMD, right? That the list of companies they will give you. They will see. One thing I'll make it very clear. Nowadays there is a slow in placement. Right? Recession is affected all the placements, not only VLSI, all the placements. I will make it very clear. Nowadays we have slow in placement, very slow. It is not only for VLSI Guru. The placement is slow all over the India only. In Europe countries already there is a layoff happening. But India layoff is not affected that much, but there is slow in placement. Even in VLSI, even in software also. Software huge layoffs has happened last month and 2 months before. Huge layoff is happened in software. So there is slow in placement happening now, even in all the domains of VLSI. That I make it clear. So what companies have visited VLSI Guru? What is the placement status? Right? You please ask in the group. They will post you in that. If you enroll, right, they'll post you in that, or you can call to the manager and you can enroll it. You can verify it. From tomorrow you can start doing that, because today is Sunday. I'm not sure about that. From tomorrow you can. So, but or else you can ask in the group. Yeah, right. So according to my recent thing, see, is there any booming in VLSI? See, I cannot tell that whether there is a booming in VLSI. But recently our central government has told that they are going to they're going to start foundries in India. Till now, we don't have sophisticated foundries in India. We are only involved in designing part. India is involved in VLSI only in designing. We don't have sophisticated foundry. All our designs are dependent upon TSMC, Taiwan Semiconductor Manufacturing Corporation. That company we are dependent upon to get the chips fabricated. Right? If the foundries are opened in India, that AMD has told that we are going to invest 500 crores in future. They have told that. Later, you should not come and ask me that, sir, you told me on that day, but where is the investment? I cannot tell on that. They have told that. I can tell you what is the scenario. Okay? They have told that they are going to invest 500 crores, more than 500 crores in India, which is already there in the right. That's already there in the newspapers, so you can refer to those things. So the central government has told that we are going to start up the foundries in India also. The few companies were already involved in that, like Vedanta and Foxtron. They broke up their MOU, so they are not continuing further. It seems, and there was again news that they will come up with the new MOUs in India. It may boom up. See, now there is a slow in placement. The reason is what situation they expected during the COVID time. The same situation didn't retain. What situation was there in the COVID time? People were not coming out. They were not using public transport. They were dependent on automobiles. Each automobile requires 15 to 20 chips for airbag control, for engine control, for glass door control. It requires more chips. There was more demand in automobiles in Europe countries. Right? They expected more improvement happens in the domain of chips, right? Chip manufacturing or chip design because of COVID. So because of that, they have done more recruitment. recruitment was done very huge. Even the Google C has told the same thing, right? But the same situation not retained, right? The situation totally changed. The situation has become normal. What we see before COVID, the same situation has become normal. Then the companies who are already recruited the engineers, right, thinking that there is more demand, so those engineers should be start working on the projects. When they move to projects, the new placements will start developing. So that is the time we are waiting for. First thing. Second thing, Intel has told clearly that we are moving from PC market to IoT. If you see in the January's newspaper, so it has already changed from PC market. It is moving to IoT. IoT also they should get the chips fabricated. But at shifting phase, I think they need a time. For that reason, there is less projects from Intel. There are several reasons like that. So for that reason, nowadays we don't have good placements or good job opportunities for the VLSI engineers. Even not only VLSI engineers, even all the domains. If VLSI is not working, the supporting roles who is done by IT team, even they'll also lose the job, right? VLSI supporting team should be done. There is a EDA development team. There is a software development team. They have to see that Unix is installed properly, Unix is working properly. There is a many teams who are working on that. Even they'll lose the jobs. So this is the reason why there is a slow in placement. That is because of COVID situation. What they expected, the same thing didn't retain. What are the job recruitment they have done? That is with over imagination they have done. And there is few shift in the projects from Intel. There are few reasons for that. That may, right, this situation may improve in future. And central government has told that they may invest few crores in foundries. If that is improving, this may improve. That is only the prediction. I'll mark it, right? It is a prediction. It is not sure it will improve. Right? It is a prediction. So placements information you can ask to the before, not this year, before February, right? Companies were asking for the candidates. We don't have candidates. That was the situation what we faced. All were placed because that was a huge recruitment was happening before February. Now we have candidates. Company is not asking. Situation. This type of situation will happen every time when there is a recession. So we have to see that whether it is going to improve. See whether there is a recession or not. If recession is not present in other domains, right, we should think about that. Even the recession is also present in other domains also. Even software also they are having recession. Because you know you are already knowing many AI tools are already available to give you the code. Right? Give me the code for D flip-flop. Tool will automatically give you the code. Chat GPT will give you. The same Chat GPT we can also do for software also. Software is totally changing, right? It's changing from developing mode to what? How to use AI tools. In that mode, they are changing. They are shifting from that. So as there are many AI tools, so even people are losing job. Now people has to start thinking how to use AI tools. Then only they'll get the jobs. Shift is happening in software domain. So there are many things happens like this again and again. You don't worry about that. If you prepare well, if you are competitive enough, you will surely get the job. Prepare well means you should be in a position to handle the live projects. You prepare well in such a way that, and you should be having good communication. You should handle the interview properly. Then you will surely get the job. See, when I take interviews, students like, sir, 1 second, sir. See, if you prepare like this, surely interviewer is not impressed, right? So you should be having good communication skill. You should communicate properly, efficiently during the interview. And if you have good knowledge, surely you'll get a job. There is nothing doubt in that. See, payment details, I cannot tell what is the payment details, what is the course fees, because you can contact to the admin or you can contact to the manager. right? They will inform you. And even EMI option, even they will inform you. I think EMI option is there, they will inform you. So first installment they will ask you to pay before the course starts or after the 1 week of course starts, and second installment they will ask you to pay before the advance classes starts. Right? So like that they may give you the option. So please contact to the admin or manager. So obviously we have this option. So the installment option is there. So please contact to the admin or manager. They will inform you. So I will give you the manager number. If you want it, you can contact him. Or you can ask in the groups also. What are the groups we have? See, class will start probably from Tuesday. See, that everything they will inform you through mail or in the WhatsApp group. If you are in the WhatsApp group, they will inform you in the WhatsApp group. If you are not in the WhatsApp group, they will inform through your WhatsApp messages, or the institute will inform through mail when the course starts. Everything they will inform you. And even if you have any queries, right, you can also contact to our manager regarding fees, installment process and all. So they will guide you. Or even you can do the message, WhatsApp message for this. They will do it. 19419, yes. Is any other doubts? Okay, okay. Thank you.